Hey there, science explorers! Have you ever stopped to think about how important sound is? It's how we communicate, experience music, and even know if danger is near. From the chirping of birds to the roar of a rocket, sound surrounds us. Sound is more than just something we hear. It's a fascinating phenomenon that involves vibrations, waves, and energy. In this chapter, we're going to dive into the science of sound and uncover the secrets behind this essential part of our world. Get ready to learn about how sound is made, how it travels, and the different properties that make each sound unique. Let's get vibing! So, what exactly is sound? Sound is created when something vibrates. Think about a drum. When you strike a drum head, it vibrates rapidly. These vibrations cause the air particles around the drum to vibrate as well. These vibrations then travel through the air as waves, reaching our ears and allowing us to hear the sound of the drum. It's not just drums that make sound through vibration. Your vocal cords vibrate when you talk or sing. A guitar string vibrates when you pluck it. Even the buzzing of a bee is caused by the rapid flapping of its wings. We know that sound is made by vibrations, but how do these vibrations reach our ears? Sound travels from its source to our ears in the form of waves. Imagine tossing a pebble into a pond. You see ripples or waves spreading out from where the pebble hit the water. Sound waves are similar. When something vibrates, it creates waves of compression and rarefaction in the surrounding medium, which can be air, water, or even solids. These waves carry energy outward from the source of the sound. Here's an interesting fact. Sound needs a medium to travel. This means that sound cannot exist in a vacuum. A vacuum is a space devoid of matter, including air, which is essential for sound waves to propagate. Without a medium, there are no particles to vibrate and carry the sound waves. It can't travel through a vacuum like outer space. In the vast emptiness of space, there are no air particles to transmit sound. This is why space is eerily silent, despite the presence of numerous celestial events that would otherwise produce sound. Remember those air particles we talked about? These tiny particles are crucial for the transmission of sound. When a sound is produced, it creates vibrations that cause these particles to move and collide with each other. They are the medium that sound waves travel through in our atmosphere. The vibrations move from one particle to the next, creating a wave that travels through the air until it reaches our ears. The particles bump into each other, passing the vibrations along like a chain reaction. This chain reaction is what allows us to hear sounds from a distance, as the vibrations travel through the air to reach us. Sound can travel through other mediums too, like water and solids. In fact, sound travels faster in water and even faster in solids because the particles are more closely packed together, allowing the vibrations to pass through more quickly. Have you ever noticed that sounds are often muffled underwater? This is because water is denser than air, and the sound waves lose energy as they travel through it, making the sounds appear softer and more muted. That's because sound travels differently through water than it does through air. The speed and efficiency of sound transmission vary depending on the medium, which affects how we perceive the sound. And if you've ever touched your hand to a wall to hear music from the other side, you've experienced sound traveling through a solid. Solids, like walls, can carry sound waves efficiently, allowing us to hear noises from the other side. This fascinating phenomenon demonstrates the versatility of sound and its ability to travel through different mediums. Section 5. Amplitude, the sound of volume. Have you ever noticed that some sounds are louder than others? This difference in loudness is due to a fascinating property of sound waves known as amplitude. Amplitude is a measure of the strength or intensity of a sound wave, and it plays a crucial role in how we perceive sound. When we talk about amplitude, we're referring to the height of the sound wave. Imagine a wave in the ocean. The taller the wave, the more powerful it is. Similarly, the higher the amplitude of a sound wave, the louder the sound we hear. Amplitude refers to the intensity of the sound wave, which we perceive as loudness. This intensity is determined by the amount of energy the wave carries. A sound wave with a larger amplitude carries more energy and sounds louder, while a sound wave with a smaller amplitude carries less energy and sounds quieter. For instance, think about a loudspeaker at a concert. The powerful sound waves it produces have high amplitude, which is why the music sounds so loud and energetic. These waves carry a lot of energy, making the sound intense and vibrant. On the other hand, consider a quiet room where someone is whispering. The sound waves produced by whispering have a much smaller amplitude. These waves carry less energy, resulting in a softer, quieter sound. Think about whispering versus shouting. When you whisper, your vocal cords vibrate with a smaller amplitude, producing sound waves with low energy. This is why whispers are soft and can only be heard at close range. When you whisper, your vocal cords vibrate gently, creating sound waves with low energy. These waves don't travel far, which is why whispers are often used for private conversations. When you shout, your vocal cords vibrate with a much larger amplitude, creating sound waves with more energy and a louder sound. Shouting generates powerful sound waves that can travel long distances, making your voice heard even in noisy environments. So the next time you're at a concert or in a quiet library, remember that the difference in sound levels is all about amplitude. It's the key to understanding why some sounds are loud and others are soft. Section 6. Frequency, Pitch Perfect. In this section, we will delve into the fascinating world of sound frequencies and how they determine the pitch of the sounds we hear every day. Now, let's talk about pitch. Pitch is essentially how high or low a sound seems to us. It's a fundamental aspect of music and speech, and it plays a crucial role in how we perceive the world around us. Have you ever noticed how a bird's chirp is much higher pitched than the rumble of a truck's engine? That's because of frequency. The bird's chirp has a high frequency, meaning the sound waves are very close together. In contrast, the truck's engine produces a low frequency, with sound waves that are much farther apart. Frequency is the number of sound waves produced in 1 second. It's a measure of how often the particles of the medium through which the sound is traveling vibrate when a sound wave passes through it. This is a key concept in understanding how different sounds are produced and perceived. We measure frequency in hertz. 1 hertz equals 1 cycle per second. So if a sound wave has a frequency of 1000 hertz, it means there are 1000 cycles of the wave occurring every second. This unit of measurement helps us quantify and compare different sounds. A higher frequency means more sound waves are squeezed into 1 second, resulting in a higher pitched sound. For example, a tuning fork vibrating quickly produces a high frequency, which we perceive as a high pitch. A lower frequency means fewer waves per second, resulting in a lower pitched sound. When a tuning fork vibrates slowly, it creates a low frequency, and we hear a low pitch. Think about a whistle versus a bass drum. The whistle produces a high-pitched sound because it vibrates very quickly, creating sound waves with a high frequency. This is why it sounds sharp and piercing. The whistle produces a high-pitched sound because it vibrates very quickly, creating sound waves with a high frequency. The rapid vibrations cause the sound waves to be tightly packed, resulting in a high pitch. The bass drum, on the other hand, vibrates much more slowly, producing sound waves with a low frequency and a low-pitched sound. The slower vibrations mean the sound waves are more spread out, giving the bass drum its deep, resonant tone. This contrast between the whistle and the bass drum illustrates how frequency affects pitch in a very tangible way. Section 7. Speed of sound, not as fast as light. While light from a lightning strike reaches our eyes almost instantly, the sound of thunder takes a bit longer to reach our ears. That's because sound travels much slower than light. The speed of sound is about 343 meters per second in air at room temperature. However, the speed of sound can change depending on the temperature and the medium it's traveling through. Sound travels faster in warmer air and slower in colder air. It also travels faster through liquids and solids than it does through air. Section 8. Sound is everywhere. From the moment you wake up to the sound of your alarm clock, to the moment you fall asleep listening to the crickets chirping outside your window, sound fills our world. It helps us communicate, warns us of danger, and entertains us with music. Understanding the science of sound allows us to appreciate the symphony of sounds that surround us every day. So, the next time you hear a sound, Take a moment to think about the vibrations, waves, and energy that went into creating it. Section 9. Sound check. Test your knowledge. Ready to test your sound smarts? Here are a few questions to ponder. 1. Why can't astronauts talk to each other directly in space? 2. Why does your voice sound different when you hear a recording of yourself? 3. If a tree falls in a forest and no one is around to hear it, does it make a sound? 4. How do noise-cancelling headphones work? 5. Why do different musical instruments playing the same note sound different? Keep exploring, keep questioning, and keep the science of sound alive.